guess it's already recording. The so let's see that. So I was looking at quizzes that we didn't do that great on. So like quiz 5 and 6, I guess, which are like, I think this is quiz 5. Yeah, quiz 5 was the nuclear power station. So it's just a balance. I don't really want to go through this today, but Kiet's going to go through these tonight for the help session. I mean, it's already worked out here, so it's not that, I mean, basically we should be able to do this. And then quiz 5 and then quiz 6 is the one on the, what was it, a freezer, making a refrigerator, ultra low temperature refrigerator with 2 cycles in it. So those are good, like, kind of examples for the final. So half of the final will be that one of those kind of problems. And there's more than just that, because each one has a bunch of examples. So you can kind of look through those. If you have problems with it, let me know. And then so that'll be half of the final. The other half will be on this chapter 18. And then I'm looking at these the example problems 5 and 6. So the Cillian diagram, basically. And then homework 3 and 4. So I wanted to go through like homework 3 and 4, then maybe if I have time, go through 5 and 6 for the same thing. And then for today, and then Kiet will probably go through these tonight, the old quizzes. That's at whenever it is, 6 o'clock, I guess. Okay, so I can go to that homework 3 first. So you put sodium fluoride into water and 10 to the minus 3 molar, and then find out what's the pH. So table 18.2 gives you the Ka for that. So you need to construct a Cillian diagram. So I want you to do this 2 ways though. So it says homework 3, also write an Excel sheet to do the calculation. So you can solve this graphically and you can solve it numerically. So you have, oops, I'm going to use another pen. Kind of a black hole here for pens, but so anyway, 10 to the minus 14 is the proton and hydroxyl concentration. That's the Ka for water, KaW. Right? And then so this is like H2O goes to H plus and plus OH minus. This is aqueous. And then the other thing, this is and this problem is adding sodium fluoride. So you have NaF goes to Na plus, and then F minus. Right, but that's the total 100% dissolution. So like HCl totally dissociates any of the strong acids or bases and these strong salts. So this is a strong base. NaOH would be a salt. This is a salt of a strong base. Which kind of tells you that this should have a pH. The final pH should be like greater than 7 of this problem. sheet in the book, he doesn't get that answer. That's kind of a problem. So this is a salt of a strong base. It should give a pH and a weak acid. Okay, because if you look at HF, let's see, I have this written down somewhere. Go to page 24. So HF, it turns out, is a weak acid. Hydrofluoric acid right here. HF, pKa is 3.17. So you have Ka for HF equals 3. Or pKa is 3.17. And then so Ka equals 10 to the minus 3.17 equals, and the reaction for HF is going to be HF goes to H plus F minus. So it's going to be H plus F minus divided by HF. Right, so that's a kind of the equilibrium for the dissociation. So because this Ka is between 0 and 14, that means it's a weak acid, and its HF is kind of right in the middle, pretty close to the middle, right? But NaOH, which would be the complement of this, would be a strong base. Right? If you look at, like, OH is the strongest base you can get, so NaOH is a strong base. So you have a salt of a strong base, and a weak acid means it should, if you just put it in water, it should give you a basic solution, right? So anyway, to make the Cillian diagram, you find 7 and 7. So you find 7 goes down and it meets 7. Then the water, so the hydroxyl, the proton concentration is going to follow from 0 to 7. So just draw that line. And the hydroxyl, so that's your H plus. And the hydroxyl is going to go from 14 to 7. Right, so you draw that line. That's your OH minus. Right, so depending on the pH, they'll balance. In other words, this continues down. So you'd have like almost no hydroxyls when you're acidic and almost no protons when you're basic. Right? And in between, if you happen to be right at neutral, then you have 10 to the minus 7 of each. That's this point. And these are decades, so this is log base 10. And then you have your concentration that you put in is whatever it said in the book, 0.10 to the minus 3. So you're putting in 10 to the minus 3. So you have this minus 3 is going to be like the kind of what you're thinking of as the baseline of this whole operation. Somewhere like that, right? So, and then your pKa is, just wrote down, they're 3.17. So you just find that point on the pH scale. 3.5, 3.25. So 3.17 is kind of like right there. So it's pretty close to the proton line. And then you're going to have your HF line is going to be when it's acidic. So you have HF here. And when it's acidic, it's going to be in the HF state. So that means you're going to have the concentration that you put in of the NaF turns into HF if it's acidic. And if it's basic, it dissociates. So if it's basic, you're going to have kind of a long region where it's basic, where you have F minus. Right? And then the dissociation of that is going to be parallel to the OH. So it's going to go off with a slope of 1. So basically, if you start here, it's going to be parallel to the OH. If you start there, it's going to have to go through uh, every decade kind of the same point, like kind of here. Right, so that's parallel to the OH. So that has to be like that. And then the acidic part is going to be just like a little bit above the H plus because it's got that shift, right? So it's going to be here. Okay, so this should come over like that. This guy goes over like this. And that's your concentration. This is F minus. And this is HF. And so that's kind of the Cillian diagram. So you have to figure out, and you know your answer is going to be basic because it's a strong base and a weak acid that you put in. So you can kind of see that you're going to be looking for an answer in that direction. In the book, he gets an answer, an acidic answer, which it's not right. So that's kind of how that went. But, so let's see. So that's the beginning of this problem, right? This is the simplest problem, right, to do. So, so then you want to write down some stuff here. And we already have the reactions. We have some things. So we want to kind of look at the knowns and the unknowns. So let me park this up here. So what are so you have these reactions. You're going to have like unknowns are going to be the proton concentration, the hydroxyl concentration. Then you added sodium, right? And you know that the sodium is 10 to the minus 3. So that one's fixed. And then the sodium dissociates into F minus, and then you're going to form HF. Right? That's it. So that's all the reactions. You have HF goes to H plus, F minus, and then you have NAF goes to Na plus and F minus. Then you have water goes to OH and H plus. Right, so H and H plus. You have 5 things, of which 4 of them you don't know. Sodium, you know, that's 10 to the minus 3. The rest of them you don't know. Right, and you also kind of know it's going to be basic. That's another feature. So you can do a balance on F. So you can do an F balance. So you have HF plus F minus equals the concentration you put in, 10 to the minus 3. You can do a charge balance. So charge balance is your Na plus your H plus equals OH minus and then F minus, because it has to remain neutral. So it's a neutrality constraint. So so then you get a problem because H plus is going to be a really small number, Na plus is going to be a huge number. And we're talking about in this plot, when you're on the basic end, H plus is going to be 10 to the minus something 7 or 8, right? And OH minus is going to be something on the order of 10 to the minus 4. So basically 4 or 5 orders difference in these values. Right? So basically, or no, Na plus is at 10 to the minus 3. So 10 to the minus 7 or 8 and 10 to the minus 3 is what, 5 orders or something? 5 orders difference, 10,000 times different. That means if you try to minimize this thing, it's not going to exactly work. So you can't solve something so small. It's like trying to find a hair in a haystack, type thing, or a pin in a haystack, but you can't find it. So, and then F minus is also going to be really large. So these two are a problem if you're trying to solve for the pH, right? You want to know the pH. You got 2 gigantic numbers, then 2 small numbers. Those 2 numbers have taken a dive in the middle. These are orders of magnitude. So compared to this number up here, right? This is 1, 2, 3, 4, 5 orders lower, right? So that's not going to work out. You can't solve that problem. You're talking about like you have 1.123, and then that number you're trying to solve for. Because that can't be done. You can solve like 1, 2 orders, but not 5. So you need to remove these guys. So you do that by taking the, you can do that with this thing. So you know that Na plus first is a fixed number. It's 10 to the minus 3. So you can just park that in there. Then you can solve this thing. This thing will be F minus is 10 to the minus 3 minus HF. Right? And HF is a small number too. So 10 to the minus 3's cancel out then. So your big numbers are gone. And then you just have H plus HF equals OH minus. Right? That's called the proton condition. And it kind of took these two constraints and made it into one constraint because some of the numbers are really big. Right? So with that, you can solve the problem graphically. Right? So basically with that, you can say, if you know it's basic, right? So you know you're over on this side of the chart, and you know H plus HF equals OH minus. You know you're on that side, then you can look and say, you can say that H plus, so H plus and HF are kind of, right? So H plus and HF are kind of the same number. You can see they're going parallel, and they're almost the same number. HF is about twice H plus, because 0.3 here, if I'm here and I go here, that's times 2, because it's log scale. So that's about what you're looking at here, is about a times 2. So basically, this is like kind of like 3 times H plus HF is going to be like 3, or it's going to be just close to HF, right? Or a little bit more than HF. And then where HF equals OH minus, that's where your solution lies. So it's going to be kind of right here. Or if you looked a little bit above where they cross, so you take the line a little bit higher and you'd have it like right about here. That would be the solution. And then you can just pick off the number. It's going to be a number like 7.2. Right, so your pH is 7.2, your H plus is 10 to the minus 7.2. And then from that, once you know H plus, you can get, well, you know the OH minus 2 is also 7.2. So basically, it kind of, you know, OH minus is 7.2 because that's where you got the cross point. Let's see. OH minus is, pH is 7.2. Your OH minus is over here. So it's going to be like 7 point, sorry. So your OH minus is on this scale. So that's going to be a little bit higher, right? So OH minus is going to be over here like that. Right? It's going to be like 7.3. So that means you can solve for HF is like 0.1, right? So, and then let's see, it's log of that. So it's log minus of that value. So you just plug in the numbers. You can read the OH here. You have the H plus from the pH value up here. And then once you have those two, you can solve all the others. So the H plus is kind of like right there. So once you have those two numbers, you can solve for HF. And then once you have HF, you can solve through the Ka for the F minus. So you have H plus and HF, you get the F minus. Once you have the F minus, you know Na. Anyway, then you know all of them, I think, right? You know H plus, you know OH, you know F minus. HF. So then you can get all those. Right, so that's how you graphically get this thing. Right. If you want to do it, with Excel, then you go. So for Excel, like 8.3, you just set up a table. So you have all the 5 things you want. Na plus is fixed. Then you have all the components, right? And then you have the proton condition, which is this business, right? Which is this business, this H, that's the proton condition that we had. There was a combination of the fluorine balance and the charge balance, right? And then you have the fluorine balance. So this two, in other words, you have 2 equations to start. You have a fluorine balance and a charge balance. You combine the two to remove the large values from the charge balance, but you still have the fluorine balance. You have 2 equations. You need 5 constraints to get 5 parameters. One constraint is Na plus equals that value. That's fixed because it totally dissociates. And you have 4 things you need. So you need 4 constraints down here. One charge balance you dropped out because you used it to get this, to get the proton condition. Then you still have the F balance, that's 2. And you have Ka, the Ka balance, which is here. That's the Kw, and then the Ka is this thing. Right, so you have those 2 conditions. That's condition 1, condition 2. In other words, equation 1, equation 2, equation 3, and equation 4 is a fluorine balance. So you have 4 equations, 4 unknowns. So it's possible to solve this. The Ka balance is this problem that these numbers are huge, right? The C9, let's see. So C9 is, let's see, the C9, these are the mole ratios, and then Ka has to equal, Ka is like 10 to the minus 4 or 5, right? So these numbers are all going to be like, you see 10 to the minus 8. So the orders are a problem because solver can only solve things maybe 2 or 3 orders. And these are going to be some huge orders. So basically the ratio seems to fix that problem. So you take the ratio of the Kas and try to set it to 1. So you calculate the Kas from the concentrations like this, and then divide it by the number that you have, which is the log of the minus base 10 of the K, or the pK, and then take log minus, or 10 to the minus of that pKa, gives you the Ka, right? So anyway, so that gives you a Ka constraint, and then the Kw constraint is 10 to the minus 14, which is, it translated that into this giant 0 thing. But basically also a ratio to get 1 because they're huge powers involving many orders of magnitude. So you have to do the ratio to solve it. And then if you do that, if you set up the equations right, so you don't use the charge balance, then you just do a solver routine. And you say, give me the value. Right. So we got it graphically pretty well, like 7.2. Right. And then solver can have multiple constraints. The C13 is, oh, it's still using the charge balance. Well, you don't have to use the charge balance redundant, but I guess I used it, but you don't need that. And then C14 is the proton condition. C15 is the F balance set to 0. Then the K ratios I put to 1. And then I just let all these variables vary, with the exception of sodium that I know what it is. Right. And I just put in the equations for the Ks, and then I just said solve, and it just spits out the answer. But all right, with the caveat that you have to start knowing the answer. So it found a solution, okay, and the answer is the same thing that I thought it would be. So 7.2, right? But the caveat of this whole operation is that if you start over here in pH 1, this won't solve it. It'll say it can't find a solution. So you have to be at the solution to kind of get the solution. So you need this Cillian diagram first. If you get a ballpark number from this, and then you set up all your things by reading this chart. It has all the 5 concentrations in it. It's got HF, F minus, OH minus, H plus, and then that's 4. What's the fifth one? And then 8 plus is fixed, right? So it's got everything you need to know is right here. So you can pick off this chart and fill in the values, and then see how close you get to the targets, and then just let it minimize it and find the actual value, right? So that's log of the C9, which is this 6.35 e to minus 8. Right, so it's got more digits than that, but so I mean I just made it limited it to 2. So anyway, so that's how you do it. So I want you to be able to do both those ways for the final. Like be able to construct this chart and then do this chart too. Right. This becomes a little bit dicier when you get to the problem. Any questions on that? I guess everyone's here. What do we have? 6 people.
Professor,
Yeah.
when we're trying to estimate that final answer, how far away does it kind of mess up Excel?
Yeah, as long as you're in base, as long as you're to the right of this, the equilibrium constant, it'll find it. Okay, as long as you're kind of to the right of it. If you're to the left, I think that's where it falls apart. So basically anywhere above pH 4, it'll probably find that solution. But you can kind of see it graphically as long as you get a rough idea. So the point of this is you got to write out first write the reaction, the dissociation reactions, including the water one. So you kind of know what's going on. And then look at the thing on the chart and say, this is a weak acid, and Na would be a strong base if it was NaOH. And then, so you know that the thing's going to have a pH bigger than 7. His answer in the back of the book is like pH 3 or something, which isn't right. Like it doesn't work. So he gets pH 3 where the HF and the proton cross, which would be the solution if you had a strong acid. I guess, I think that would be like the strong acid solution, but you don't have a strong acid. All right, even though HF is an absolutely deadly material, like HF is the worst acid, but it's a weak acid. So the reason it's deadly is that it can pass right through your skin or through your eyeballs. Like it's small enough that it can just pass into your system. And then the fluorine somehow reacts with the calcium in your bones and in your bloodstream, takes all the calcium out of your body. Somehow fluorine reacts with calcium. It's the electronegativity. It's like the most electronegative or something or other. But it sucks up all the calcium out of your blood. Your brain needs calcium to function and your heart needs calcium to function. So you immediately die. Like 1 drop of this will kill you. If you get 1 drop of this on you, the thing to do is to cover yourself in calcium gel, and that will suck up the fluorine. But basically, this is one of the most deadly chemicals, and it's cheap. Okay, so it's used in the petrochemical industry as a replacement for HCl, believe it or not. So there's one plant in California, in the city of Los Angeles, that's the only large plant where they use large amounts of HF, and it's right in the Torrance, California. It's like right in the city of Los Angeles. So, I mean, there's a lot of oil on the West Coast, and they actually pump oil right out in the city limits. The tar pits and things are all oil fields in the city, and they refine it right there. And they have a big plant that's got a huge HF processing in it. It's probably the only place, but also they have the highest regulations in the country, the strongest regulations. So I guess it's safe, but if you use HF in the lab, you got to make sure you have calcium gel, like big supply of it, and putting water to wash it off doesn't solve the problem. It makes it worse. It actually flushes it into your system. So it's like jumping in a swimming pool or something will make you die faster. So basically, they're showing these chemicals never say like this is really deadly. But it's a weak acid though, so it's kind of surprising. You think like it's so dangerous. Why is it so dangerous? It's not because it's a strong acid. So anyway, yeah, as long as you're over here, it'll solve it. You might just have to try to get it right. But it will find this over here. So this similar, this is almost the same as the acetic acid. So they do sodium acetate in example 18.5. It's almost exactly the same thing, except they don't do the Excel thing. So I think it's worthwhile doing the Excel thing because you can actually solve this thing with Excel. He shows the Excel thing for the last problem with ATP or something. I forget what the last example problem is in the chapter, but he uses Excel to solve it with the free energies. But basically all these you can kind of solve with Excel more or less, but except for the problem 18.4, which doesn't exactly work very well. Let me get rid of this thing. That's the grade sheet. So I wanted to do 18.4 then too. So any other questions on this? That's a good question. Like, I mean, if you put the pH way out at 14, it also won't solve it. It'll find some other. It's a little tricky actually, because you have big numbers. So the big numbers, it's kind of hard to. There's big and small numbers. There's many orders of magnitude floating around here, so it becomes a difficult thing to minimize by these scores.
Yep. I also noticed that it's kind of close to where we have our H plus value on the chart. So is that something we can use going forward?
It's different for every system.
Okay.
Two are the same. That just happens to be where this pKa is. If the pKa is over here, then they're different. So every system you have to start from the beginning and write down and go through. It's not, I mean, there's kind of a generic method, but basically every system you should just take it new. And you go, oh yeah, I can do this, I can do that. But basically start fresh and try to think about it. This Cillian chart definitely helps a lot. It gives you kind of a picture of what's going on. Otherwise, you'll miss out that something is going to be many orders of magnitude different in size. And if you miss that, then you miss the whole point of it. So, it's kind of strange. Like I looked in a bunch of books on electrolytes. This is the only book where they use Cillian charts, right? And they call them different names. And this chart had different names in different books too. So, but it's really useful. Like it's good that he put it in there because it makes it make a lot more sense. So, but if you look in, I put a bunch of electrolyte books on the webpage, like this, one of them that's really good is this, this handbook of aqueous electrolyte thermodynamics. It's kind of written, it's almost typewritten. So it's an old book, but it goes through industrial processes, like sulfate removal from flue gas and chlorination of water. So it's good. I think that's the best source, but there's all these other kind of analytic chemistry or physical chemistry books. Pitzer's book is good too. The other ones like ionic equilibria, bioprocess engineering is just a bioprocessing book for fermentation. They use redox reactions, so it's just a reference. So, but anyway, the other ones are like the right is kind of the main reference people use, like a wiki page uses, and it doesn't have Cillian charts, and it isn't really that useful of a book. So that's the main reference for electrolytes. But anyway, so why don't I go ahead and do, unless there's more questions, but I'll go ahead and do the other one, which is 8.4. So he's putting in two things. So this one he's putting in sodium bicarbonate. So it's baking soda, right? NaCO3, HCO3. Then he puts that in with HCl, which is a strong acid. So the HCl just goes directly to H plus and Cl minus. And so it's just a source of H plus and the concentration of that. So the concentration of Cl minus is fixed at whatever the concentration was. You could find that, I guess you see HCl at the top of the chart, so it's in strong acid. So those totally dissociate. Right? And then same with the strong bases. So you have OH minus NaOH. It's just going to totally dissociate. Or these sulfates, or so all these things will just dissociate. Amines. So those just say like there's no balance of it. It just goes because they're more acidic than water. So in that case, water rules, and then they just totally dissociate, and then water buffers the thing. Water's like the salt that buffers it. So let's see, the HCl carbon concentration, Cl concentration is 2e to the minus 3 molar. It's moles per liter. So and then the NaHCO3, it's a strong base, so that one's going to go completely to Na plus, and then HCO3 minus. So this is going to have like a lot more components because the HCO3, so this is the same thing as carbon dioxide dissolves in water, and then there's a whole series of reactions that happen. Right, so this HCO3 minus can dissociate into H plus and then CO3 minus 2. And then you can have CO2 just from the air, and you have to add water, and then let's see, what is this reaction? This is this is reaction here. So here you have H2O, CO2, H2CO3 goes to 2H plus 2HCO3 minus. Oops, that would go here. I'll just make these as concentrations, so you can kind of just have one symbol. So this guy is here. So this is written as an acid reaction, even though it's a base reaction for our case, because we're feeding in the HCO3 minus, and then that's going back into H2CO3, which is neutral, and carbon dioxide and water. You need the water to make this balance out. So water's there anyway. It's water, aqueous. It's just, it doesn't count in any of the reaction conditions. And if you look in the table, so they just do CO2, H2CO3, they don't use the water, and they don't show the proton coming off over here, and they don't put the 2. So they just give the equilibrium constant 6.351. So this is Ka 2 equals 6.351, or pKa 2, and then pKa1 equals the what was it? HCO3 minus is somewhere here. Here, HCO3 minus to CO3 minus 2 is 10.329. Okay, it's 10.329. Right, and then you also, so these things will have their, I mean, you'll have like H plus times CO3 minus 2, no, not squared, divided by HCO3 minus. So this one will have, in the charge balance, will have a 2 in front because it's minus 2. This pKa will be, so these are all, this is liquid water, so that's 1. Usually your dilutes, you call that just 1. So that drops out of the equilibria. So this is H plus squared because it's 2, and then this is HCO3 squared minus squared, and then CO2, then H2CO3. Right, those are your balances for this thing. I mean, so those are like equation 1, equation 2. Then the unknowns that you have are a lot. So you're gonna have like your Na plus, which equals, let's see, the amount of Na that they put in. Sodium 1 e to the minus 3. The carbon is 1 e to the minus 3. So this thing is 1 e to the minus 3. Carbon, because that's the only source of carbon. So the total carbon is 1 e to the minus 3, same as Na plus. Then you're going to have like Cl minus, that one's fixed too, is 2.2 e to the minus 3. And then H plus, OH minus. H plus is the thing you want to solve for. And then you have HCO3 minus concentration H2CO3, CO2, and then CO3 minus H plus, H2CO3, CO2, water doesn't count. Oh, and then CO3 minus 2. Right, so those two are known. You have 6 things you need. So you need 6 equations to solve this. Right, you have 6 unknowns, 2 knowns. And you need 6 equations. You have 2 Kas, and you have Ka water equals H plus OH minus equals 10 to the minus 14. So that's equation 3. So you need 3 more equations, right, to solve it. So we're going to get the equation. So there's going to be, you can do a charge balance if you want. So you have Na plus H plus, those are all the plus guys, equals Cl minus, and then plus OH minus, plus HCO3 minus, and then plus 2 times CO3 minus 2. See, this is where the 2 comes in. So that's a charge balance. And then you can do a carbon balance. So you know that all the carbons have to sum up from what you put in. So the initial carbon that you put in is the Na, 1 e to the minus 3. 1 e minus 3 equals, and then you can just go through, find your carbon. So it's going to be HCO3 minus plus H2CO3 plus CO2 plus CO3 minus 2. So the CO2 is the only thing that's going to, so all the ionic species are dissolved. So CO2 is the only one that's going to be in, or let's see, CO2 and the H2CO3 are going to be in equilibrium because they're dissolved uncharged. So those two will be in equilibrium with CO2 in the air. So these two are kind of coupled together. Oops. The H2CO3 and CO2 are coupled together because they're dissolved in the water. They're not charged. So you're going to have the water, the CO2, the H2CO3, and then CO2 in the air. So vapor and liquid. So you're going to have a Henry's law constant that relates, that gives you the partial pressure of CO2 over this, like Psat. Psat times this Henry's law constant is going to be the pressure. Right, so basically, Henry's law constant will give you the partial pressure. It's going to be pressure times the Y composition of CO2 in the air. So if the air composition is, I think it's 0.003 or something in the air CO2, then if your number for this comes out larger than that 0.003, then that means you're going to make carbon dioxide bubbles and your soda will bubble. And if your number is smaller than that, it won't bubble. So that's the idea of like, is it going to leave this solution or not? Depends on what's in the air above it. The other thing about this is that this number is like the atmospheric number that you're increasing when you burn fuel, right? So the CO2 production from combustion is boosting this number. That's what's acidifying the oceans. So as you increase the CO2 in the air, then the Henry's law constant will give you increase in the CO2 dissolved. And the CO2 dissolved goes through these reactions and makes acid. Right? That increases the pH of the ocean, kills the coral. Basically, that's what's killing off the Great Barrier Reef and all that business. Right? So these reactions are important in a variety of situations. One is like environmental, because a lot of electrolytes involved. Environmental, then biomedical, because this is all the balances that are taking place in your blood, and then industrial. So a lot of the wastewater treatment and freshwater treatment, and then like basically corrosion, right? So these kind of things are going to be like everywhere. So anyway, so we can make a Maxwellian diagram of this guy. So we know the so that's kind of where we are with this. So we can just start this thing over. So you're always going to have this water balance. You're always going to have, so you just plot this on it to begin with, I guess. So the water, the H plus and OH have to be on it. So it's H plus. And the OH one's here. And then we have our concentration of the let me get his answer up, because that's going to make my solution right. So we have the 10 to the minus 3 was 10 to the minus 3 is an Na. So that's what we put in this carbonate, right? So we're kind of buffering it with HCl. So we're dumping in HCl. It's really like a carbonate balance we're looking at. So that concentration is a 1 e to the minus 3. Anyway, the Cl is 2 e to the minus 3. So they're close to each other. But our baseline here is going to be 1 e to the minus 3. So basically just along this line. So that's kind of our operation zone, is the concentration that we put in. I'm just going to kind of darken that one, so you kind of know what we're working with. And then we can put in our Ka values, right? So we have our pKa. So we got pKa for number 2 is 6.351. So 6.5, 6.25 is here. I'm looking for 6.351, should be like right there in between. And then so that's for 2. I call it reaction 2. And then the other one is at 10.329. So 10 is here, 10.5, 10.25, 10.329 is kind of like right there. So that's reaction 1, what I call reaction 1. Right. So then I can draw my components on this thing. So I have I have over here, there's going to be CO2 and this is this reaction. That's this reaction. So CO2 and H2CO3. Right, that's reaction called 2. Yeah. So if we're at a low pH, that's going to be, all the material is going to be in that state. And then in between, that's going to degrade into HCO3 minus. Right? So in between, we'll have like HCO3 minus. Then the HCO3 minus degrades into CO3 minus 2. So that's like way out at high pH. Right, so, and then the acid is going to go, so this is kind of the HA, this is HA for that one, and this is the base. Right, so the acid is going to follow the H plus line it's going to be parallel to it, meaning that, and these are all like, in other words, it's going to be 1 decade by 1 decade. They're just going to be lines until they get to the other reaction. So once it reaches the other reaction, it becomes 2. So if you went over that far, then you'd go over that far, and then you go over the same distance for all the decades, and that would be your line for the acid. Something like that. Right? So just put it in here, except that this thing, once it reaches this base, so once it reaches that point, has to go twice the slope. So it's going to just take a turn for the worse like that. This part isn't right. And so once it reaches the other equilibria, then it's Ka1 times Ka2. So the slope here becomes twice as much. But we aren't really dealing with that, so it doesn't make any difference. Right? But basically, the slope is 1, and then it goes to 2. And then when it gets up here, this will go to about a decade away from that. So we can write this in terms of an equation, but basically, for the purpose of the Cillian diagram, we don't need an equation. We don't need a stinking equation. Right? So we can just kind of sketch it in. And then this guy's kind of flat here, and then he's going to take a dive down, right? And it's going to go through that point, and it's going to have a slope of 1, meaning that every time it's going to have to go to there. Get this right until it gets to the next thing, but there is no next thing there, so that doesn't matter. So that should be a line, but someone messed it up. Oh, I put it in the wrong place. It should have been over here. Let me just put this over here. Put those all in the wrong place. That's right. So that guy should go like that. And it's going to have this sweeping thing here. And then, so the other one, same thing. So it's going to be like same point every decade. So there's only a couple decades there. So it should be like that. And then this will curve over. And then this one, this guy will be flat here. And then he's going to follow this like that. So I'm putting the mark the same distance over for every decade. Oh, and then once it reaches here, it also goes to steeper. Once it reaches the other equilibrium, it's got to go over. Okay, so so let's see. So now you have to do all the balances on this. We're kind of out of time. I mean, he pretty much explains it in the answer book. I'm not sure if I'm going to give like one like this or one like the simpler one. It depends how long it takes to do this. This one is also done in the book as example 18 point. What? It's down somewhere. Book. (18.6). Like example 18.6 is phosphoric acid. It's doing the same. This is the same thing. It gets the same kind of plot, right? Except this, I think the phosphoric acid doesn't have. It's just pure phosphoric acid. It isn't with a HCl added or anything. Yeah. So anyway, the answer. It's just phosphoric acid put in water. So there's no HCl. Oh, he does add HCl. So he adds HCl. So that just complicates the balance, right? You know the HCl, the Cl concentrations, that isn't an extra parameter, but it's just the pH of the system. So you have to add it into all the equations and then just do the calculation for it. So you have to, yeah, there's a lot to do with this. Actually, it's going to take another half hour, so I don't really have time to go through it. We'd write down all the equations again, and then figure out in the range where we have to go, which is going to be, this is a weak, this is again a weak base. So this thing has to have a basic solution above 7. When you look in the 7, you find out that the species that are important are like CO3 minus 2, and then the others like orders of magnitude away. So basically you can solve the thing by looking at the chart and figuring out the range you're going to be in, and then just after writing the balance equations, drop out terms, and then the solution becomes pretty clear. It's where one of these, I think the solution is like right here, like pH 8 something. It's where the acid meets the OH line. OH equals the CO2 stuff. I think that's the solution for this. So anyway, so it just comes out of the equations. He goes through it in the answer sheet, how to get that. Oh, wait a minute. I guess I got that wrong. Anyway, it's basically that scheme, like the parts fall out and you get the pH. I guess the pH of this thing, oh, this one doesn't dissociate at all. That's right. This one is just like straight up CO2, H2CO3. And then because of that, anyway, he explains it here. Let's see, what does he say? The charge balance, combined with the materials, this is a proton balance. Then these terms drop out. So the 2 from the Cl and the 1 from the sodium cancel each other. So you get a 1 term. And then in the region where this could possibly, so you see like this, so H plus, the most it could be is going to be 2 e to the minus 3. It's like, so basically that can't be possible because it's not intersecting any of the other compositions. So if you follow that down, the first possible solution could be right here. And then if you look at all the other components to that equation, to the proton equation, H plus is going to be a large number. This could be a large number. Then CO3 is going to be 0, right? It's got to be like really small. And then OH is also following the CO3. They're both going to be really small. So basically this ends up being that H plus and the CO3 have to equal 1 e to the minus 3, which is a line that you have. So this basically the intersection has to be at this point, the way this equation works out. HCO3, CO3 minus OH minus. I guess all these numbers are small and it ends up H plus just has to be e to the minus 3. Like that's where it has to end up, because these numbers would be too small to make any difference. All of them are too small to make any difference from this chart. Like everything is at least 2 orders of magnitude smaller than H plus. Actually 3 orders smaller than H plus. And these are like, so the CO3 is going to be like 8 or 9 orders smaller. So those terms don't contribute. And the OH is also getting worse and worse. So all these 3 terms drop out and H plus is just 1 e to the minus 3. So the pH is 3 for the solution of this. If you try to do this in Excel, the problem is because all these numbers are 0, you can set up an Excel sheet for this guy the same way. It's more complicated. But wait, with this particular problem, like maybe if you didn't have it set up with the HCl, so it wasn't basic, if it wasn't acidic, if it's basic, then you can solve it. If not, you can't really solve this thing because it gets to be, even if you mess around with this, so this is just set up with the KAs, then the charge balance, proton condition, then all the other balances, right? And then just minimize the 6 concentrations that you have. But most of these are like so small that they don't, like 10 to the minus 14 doesn't help. Right? So actually this isn't minimized the right way, but basically if you minimize this the right way, you find out that it's like, it won't minimize it. It'll just crash out because it's got parameters that it can't solve because there's many orders of magnitude smaller. So deviations in those don't matter. So the solver can't solve it. So, so the solver routine would only work like in certain parts of this chart. Like when you're way down here, solver won't work. But in that case, there's just a simple solution to it. So that thing goes off all the time. Anyway, I'm going to quit there. So hopefully that's okay. Any comments on this or questions or anything?
So for this week, I noticed we have no team, no groups for the homework, so it's just individual.
Oh, no, the homework is still the same group thing. Can you use last week's group for the homework? I didn't realize there's no homework group. I forgot to add that in. I can add in another one, but maybe we just use the homework group from last week.
All right,
Sorry.
sure.
Yeah, I
But
totally forgot about that.
you probably have to send an email to the rest of the class, though.
Yeah, I'll send an email.
Okay.
I'll send it right now. Yeah, so, but it shouldn't be too bad. Like, it's just like the answer sheets are here, so it shouldn't be bad to put together something. You can kind of look through it. Anyway, for the final, you should probably look through, especially 3 and 4. The others kind of follow. They aren't much more difficult, you know, the same idea. So in fact, the others might be simpler than the first two, but the first two seem to have most of the information for this thing. So it's good to just kind of get that. And the others, you can see how they do it. Like this one biology question, and there's something about soda, like the carbon dioxide in soda. They're pretty simple, actually. They're simpler than this. There's no acid, there's no Ka for the thing that you're using. You just do the straight lines, the concentrations. So anyway, this is easier, I think. This is harder, the others are easier. So anyway, yeah, I'll send out that email. Sorry, I forgot to do that. All right, thanks. Any other things? Okay, so I'll see you later. Thanks.